We have ignition and liftoff.
Some chemical reactions are pretty obvious. Other reactions can be hard to spot. But the same reactions that can get us into orbit can also get us across town.
Engine set 100% and throttling down.
Chemical reactions can be spectacular, but they can also be everyday events. My body runs on chemical reactions, so does my CD player, and my car too. So what kinds of reactions are there, and how can we tell a reaction is happening? How do we name and classify the compounds involved? And how do we describe a chemical reaction through a balanced equation? The business of reactions is simply the business of science.
How do you know there's actually a chemical reaction going on? What evidence would you look for?
A chemical change occurs when existing bonds between atoms break and new bonds form, producing new substances.
Do you think applying heat to these ice cubes will cause a chemical reaction?
Well, the ice will change from a solid to a liquid to a gas.
But it's still H2O. It's just changed its phase.
Right. The bonds haven't been broken, so it isn't a chemical reaction.
Good thinking. So a phase change or physical change doesn't alter the chemical composition of a substance. The evidence for a chemical change can include one or more of these: an energy change, a color change, bubbles forming, a precipitate forming, a change in odor.
An energy change in a chemical reaction can be exothermic, which releases energy, or endothermic, which absorbs energy. This reaction is obviously releasing energy in the form of light and heat. There's an exothermic energy change, and that's evidence of a chemical reaction.
Watch what happens here. When we mix these two colorless solutions, a yellow substance forms. We see a color change and a solid precipitate forms. Both are indicators of a chemical reaction. When we put sodium metal in water, bubbles of gas form. Gas bubbles are evidence that a chemical reaction is going on.
Pure sulfur doesn't smell at all.
But when the sulfur in a match head burns, there's light and heat.
As well as an odor that's really powerful.
The change in odor shows there's been a chemical reaction.
Remember, no matter which chemical reaction you may be observing, always look for one or more of these indicators.
Sometimes a reaction will create complex chemicals out of simpler ones. How do we know? By the evidence. For instance, this is what happens when hydrogen burns. It's the reaction you see when the main engines of the space shuttle fire up. What's the evidence? Obviously, lots of heat and light are given off here. It's an exothermic energy change. The product that's formed, H2O gas, is more complex than the reactants. That's why we call this a formation reaction.
A formation reaction causes two or more elements to combine and form a compound.
Let's burn this solid magnesium and see if there's evidence of a formation reaction. By the way, when magnesium burns, it gives off dangerous amounts of light and heat, so we need to take precautions. So what was happening here?
The magnesium was reacting with oxygen in the air.
There's definitely an exothermic energy change. It gives off heat and light.
And the product left behind is this white powder. So there's a color change.
Right. It's solid magnesium oxide.
We have clear evidence of a chemical reaction.
And since two elements have been combined, it's a formation reaction.
Right.
Formation reactions are widespread in industry and technology. Fuel cells in the space shuttle use the formation reaction of hydrogen and oxygen to produce electricity and pure water, both very useful in space.
On course for a 57-degree orbit.
Fuel cells also power these buses. Since the only products are energy and water, they limit air pollution. But some formation reactions are undesirable, and we try to control them. For example, nitrous oxide and carbon monoxide out of car exhausts, sulfur dioxide out of industrial smokestacks, and rust.
Are there formation reactions that happen naturally without any human activity?
Sure. Most minerals are formed from chemical reactions or formation reactions. Now, a mineral is any naturally occurring inorganic substance with a definite chemical formula and usually a definite physical property or crystal structure. And minerals are the constituents of all of the rocks that we see outside.
Why are some minerals more valuable than others?
Well, a mineral is only valuable if its chemical or physical properties are of use to society, such as diamonds or gold being worn as jewelry, or aluminum in a mineral. We can extract that and turn it into airplane wings and so on.
I've heard of some famous mineral discoveries such as the Klondike gold strike.
That's an excellent example. In fact, there are many mineral discoveries in Canada that are economically important, such as the nickel deposits in Sudbury and a new nickel deposit that's been found in Voisey's Bay in Labrador, uranium in northern Saskatchewan, and even diamonds in a rock called kimberlite in the Northwest Territories.
What chemical processes in the earth form such valuable minerals?
Most of them are things like precipitation from a hot fluid, or evaporation from things like seawater, or crystallization from a liquid rock, which is also called magma.
What kinds of minerals do geologists watch for?
Well, geologists look for minerals called indicator minerals, which are sort of linked to the minerals that are economically important. Things such as quartz and gold, as an example. Although quartz is found with gold, quartz is very common, so it's not always an indicator that there's gold there.
As you know, a compound contains two or more different atoms chemically bound together. But it's possible to classify compounds more precisely using diagnostic tests. To get consistent results from experiments, scientists use SATP, Standard Ambient Temperature and Pressure. At SATP, materials and their surroundings are at a temperature of 25 degrees Celsius at an air pressure of 100 kilopascals.
We have four compounds here: potassium chloride, ethanol, sodium hydroxide, and hydrogen citrate. Now, which classification would you predict for these compounds? Ionic or molecular?
Okay. Potassium chloride, KCl solid, has both a metallic and non-metallic ion in it. So it must be an ionic compound.
Ethanol is C2H5OH liquid. It doesn't have a metal in its formula, only nonmetals.
That's right. Hydrogen isn't considered a metal.
So ethanol is a molecular compound.
Sodium hydroxide, NaOH solid, has both metallic and non-metallic ions in it. So it's ionic.
And hydrogen citrate is C3H4OH, COOH3 solid.
It doesn't have any metal in it, so we predict that it's a molecular compound.
Good work. We'll test your predictions and see how they hold up.
The solutions of some compounds can be classified as acids or bases according to their pH level. pH is the acidity or alkalinity of a substance. It's measured on a scale from 1 to 14, with 7 being neutral. Acids have a pH less than 7, and their solutions contain hydrogen ions. Bases have a pH greater than 7. Their solutions contain hydroxide ions, polyatomic ions which stay together during chemical reactions.
The simplest test for acids and bases uses litmus paper. When exposed to acids, blue litmus paper turns red. And when exposed to bases, red litmus paper turns blue.
We're testing our 4 compounds to see if our predictions were right.
The tests are state of matter at SATP, solubility in water, conductivity of the solution, and pH of the solution.
The test results will put the compounds in one of 4 possible categories. Neutral ionic compounds are all solids at SATP. They usually dissolve in water, form conductive solutions, and have no effect on red or blue litmus paper. Neutral molecular compounds can be solid, liquid, or gas at SATP and may dissolve in water. They form non-conductive solutions and have no effect on red or blue litmus paper. Bases all dissolve in water, forming conductive solutions. They turn red litmus blue, but have no effect on blue litmus paper. And finally, acids all dissolve in water, forming conductive solutions. They turn blue litmus red, but have no effect on red litmus paper.
Potassium chloride is an ionic solid at SATP.
It dissolves in water, so it's soluble.
It conducts electricity.
There's no change to the blue litmus paper.
And no change to the red litmus paper.
So how do your observations compare to your predictions?
We predicted an ionic compound. Our prediction matches the test. Solid at SATP, conductive solution, neutral pH.
Good.
Ethanol is a molecular liquid at SATP.
We know it forms a solution with water. We can't see any separate layers.
The solution is not an electrical conductor.
There's no change to the blue litmus paper.
And the same with the red litmus paper. No change.
So our prediction agrees with the tests. Liquid at SATP, non-conductive solution, and neutral pH.
Which is evidence that ethanol is a molecular compound.
Right so far.
Sodium hydroxide is a solid at SATP.
It dissolves in water, forming a solution.
The solution is an electrical conductor.
There's no change of color on the blue litmus paper.
But the red litmus paper turns blue.
Which means a high pH level.
So can we be more specific about its classification?
Can we say that it's a base?
Absolutely. That's what it is.
Last, there's hydrogen citrate, a solid at SATP.
It dissolves in water, meaning it forms a solution.
The solution conducts electricity.
The blue litmus paper turns red.
And the red litmus paper shows no change at all.
So how would you classify hydrogen citrate?
We predicted a molecular compound.
But the solution was conductive, which doesn't fit with our prediction,
And the red litmus paper turned blue.
which tells us that it has a low pH level.
So that means?
It's an acid.
Very good.
In their pure state, acids act as molecular compounds, but in solution, they show some properties of ionic compounds, like conductivity. That's why acids are classified in a unique category of their own.
Why are valuable minerals found in some places and not in others?
Well, valuable minerals can be found in many different geologic environments. Basically anywhere where the situation exists that you can collect and concentrate the constituents of that mineral. Some good examples are in volcanically active areas. The magma has mineral constituents in it that can crystallize out and so on. And the fluids associated with the magma also act in a similar fashion. Seawater brines can evaporate, producing minerals. And things called black smokers, which sit on the bottom of the ocean floor, are basically chimney-like structures that jet 400 degrees Celsius water out with a whole bunch of solutes in them. They precipitate out in the cold seawater and form mineral deposits around those black smokers.
The law of conservation of mass states that matter cannot be created or destroyed. In practical terms, this means what goes in must come out. Atoms are not created or destroyed in a chemical reaction. They're still present, but in different combinations. So to balance a chemical equation, the number of atoms present on the reactant side must always equal the number of atoms present on the product side. Knowing this, how would you balance the reaction for the formation of water?
Okay, we know that hydrogen gas plus oxygen gas react to produce water vapor plus energy.
But the equation isn't balanced. We have 2 hydrogen atoms and 2 oxygen atoms on the reactant side, but on the product side, we have 2 hydrogen atoms and only 1 oxygen atom.
Every atom that exists on one side of the equation has to exist on the other.
So we put in coefficients to get the same number of atoms on each side of the equation.
Okay, so we need 2 oxygen atoms on the product side. We'll make that 2H2O.
Now we need 4 hydrogen atoms on the reactant side. So let's make that 2H2.
So now we have 4 hydrogen atoms and 2 oxygen atoms on the reactant side.
And 4 hydrogen atoms and 2 oxygen atoms on the product side.
So the equation is balanced.
How would you balance the equation for photosynthesis?
Okay, the simple equation for photosynthesis is carbon dioxide gas plus liquid water plus energy reacts to produce glucose solid plus oxygen gas.
So on the reactant side, we have 1 carbon atom, 2 hydrogen atoms, and 3 oxygen atoms.
And on the product side, we have 6 carbon atoms, 12 hydrogen atoms, and 8 oxygen atoms.
So it definitely isn't balanced.
What's the right way to do this?
Look at the most complex compound first and leave pure elements to the last.
Okay, let's start with the glucose molecule. So we need 6 carbons and 12 hydrogens on the left side.
So we give CO2 the coefficient 6 to give it 6 carbons.
And you give H2O a coefficient of 6 to get 12 hydrogens.
That balances the carbons and the hydrogens. But what about the oxygens?
Now we have a total of 18 oxygens.
If we look at the glucose molecule, we can account for 6 oxygens, which leaves 12.
So we can balance the oxygens by giving O2 a coefficient of 6.
That works. We're balanced.
Good work. The solution may not always be simple, but it's always possible to balance the equation.
So now that your equations are balanced, how would you name the compounds involved? Using the IUPAC rules, simple ionic compounds are easy to name. For example, how would you name an ionic compound with the formula CaF2? Well, the metal name comes first, calcium, and the ending of the non-metal name in a compound changes to "ide", so fluorine becomes fluoride, and CaF2 is calcium fluoride. The IUPAC rules use a prefix system to name simple 2-element or binary molecular compounds. Prefixes indicate the number of each type of atom in the compound: mono, di, tri, tetra, penta, hexa, hepta, octa, ennia, deca, and so on.
When we're naming molecular compounds, we add prefixes and change the ending of the second element to "ide". For example, the molecular compound P4O10 has 4 phosphorus atoms, which is tetraphosphorus, and 10 oxygen atoms, which is decaoxide. So, P4O10 is tetraphosphorus decaoxide. Of course, many molecular compounds also have common names. For example, water, sugar, ammonia, and propane.
Balancing a chemical equation tells us exactly what goes in and what comes out, and naming lets us communicate the compounds involved. But the products of a reaction aren't always more complex than the reactants.
In a simple decomposition reaction, compounds are broken down into their component elements.
This Hoffman apparatus has been running for a while.
By sending an electrical current to the electrodes, we've been adding the energy needed to decompose water to its component elements.
One of these is hydrogen gas, and the other is oxygen gas. But which is which?
We could do the glowing splint test, but we can also figure it out by balancing the decomposition reaction equation.
Right. H2O liquid plus electrical energy react to produce hydrogen gas plus oxygen gas.
To balance the equation, we need 2 atoms of oxygen on each side.
So we add the coefficients. 2H2O liquid plus electrical energy react to produce 2 hydrogen and 1 oxygen.
The balanced equation shows that twice as much hydrogen gas is produced as oxygen gas.
And that's what we see in the Hoffman apparatus. There's twice as much gas on one side as on the other.
So this must be hydrogen, and this must be oxygen.
In submarines, electrical energy from batteries or nuclear power plants can be used to decompose water, producing oxygen for the crew during long underwater voyages. That's just the opposite of the formation reaction used by the main engines of the space shuttle.
Can you give me an example of a decomposition reaction involving a metal?
Sure. Probably the best example is the smelting of aluminum from a mineral called bauxite. The bauxite, when it's mined from places like Jamaica, is brought in and crushed up into a fine powder. It's mixed with another mineral called cryolite, and that mixture is melted at about 1,000 degrees Celsius. And then an electrolytic process, similar to the Hoffman apparatus, separates the aluminum oxide into aluminum and oxygen, and the aluminum is then drained off. Now this process requires a lot of electricity, and there's a plant near Montreal actually that uses as much electricity in a year as the entire city of Montreal.
Yo, let's rap.
So, experimental evidence helps us classify reactions and compounds more precisely, and sometimes the evidence challenges our predictions. But even if reactions don't let everybody conquer space, they can certainly help us get from A to B, And that's simply science.